Let's take a look at this example. This is the kinematic, rectilinear kinematic problem, the erratic problem, and we will see that the car has the motion that is defined by st graph, like like this like this picture. Okay, we can see that this is the erratic motion because the motion is cannot define by only single function. It's defined by two functions, that is from from time equal to 0 to 5. Okay, from time equal to 0 to 5. The position is defined by this equation, that is s equal to 3t squared. And from time equal to 5 to 10, from time equal to 5 to 10, the position is defined by this equation instead. That is the linear function is s equal to 30t minus 75. Okay, so because it is the erratic motion, we would like to find the VT graph and AT graph, okay, in order to explain the motion uh, of of the car, specifically in terms of velocity and acceleration for each interval. It is better to plot the graph instead of show in the function. Okay, so then to this problem, if we would like to plot the VT graph and AT graph, we will recall the relationship that we already know. Three main kinematic equation that we have: V equal to dS by dt and A equal to dV by dt. Okay, so for this case, we have ST graph. We would like to find VT. So then we will use this relationship, that is the slope of ST graph, the slope of ST graph, that is dS by dt, is equal to V, velocity at any time. Okay, so then we just find the slope. Okay, so for this case, you see that we have the time interval from 0 to 5 seconds, from 0 to 5 seconds, like this. According from time equal to 0 to 5, we know that the position is equal to 3t squared. Okay, so when we would like to find the velocity at this interval, we take the first derivative of the position and we get the velocity function equal to 6t for time equal to 0 to 5. 6t, what does it mean? It means that velocity is the linear function 6t. Okay, this is the linear function. 6 is the slope of the graph. Okay, the graph is the linear with the positive slope, so then the graph should be like this. Okay, so then we use this to construct the VT graph from time equal to 0, t equal to velocity equal to 0, from time equal to 5. Okay, v equal to 6 multiplied with 5, it becomes 30. That is, we have the linear function like this. Okay, this is the first period. For the second one, when time equal to 5 to 10, we have the position function defined by this function, that is 30t minus 75. This is the linear function. So then we take the first derivative of this function to obtain velocity in this interval. So because this is the linear function, when we take the first derivative, we obtain the constant value of 30 meters per second. Okay, so then for this interval, it means that velocity become constant from this interval of time. Okay, from time equal to 5 to 10 seconds. Velocity is become constant. That is equal to 30 meters per second. Okay, now we already done VT graph. Okay, next we will determine the AT graph. Okay, for the AT graph, we know that acceleration equal to dv by dt. Okay, so that means that the slope of the VT graph, is equal to the acceleration. Okay, the slope of the VT graph equal to the acceleration at any time. So then for the first interval, that time from 0 to 5, okay, we have the velocity function equal to 60. Okay, so then A for this interval is equal to constant, that is 6 meters per second squared. Okay, so then we can construct the acceleration like this. It is a constant acceleration in this interval. Okay, and if we consider next period of time, that is from 5 to 10 seconds, the acceleration is become 0 because the velocity at this interval is equal to constant 30 meters per second. So after we take the derivative of the constant, we obtain 0. So then for this period, it means that it has no acceleration. That is, acceleration is equal to 0. So then let's we complete the AT graph like this. Okay, that's all for this example. And if we take a look to the next example, that is maybe more complicated. That is this is not the AT and VT anymore. It is the VS graph. Okay, for the case of VS graph, that is we may not familiar with. Okay, so we have the VS graph that is describe the motion of the motorcycle, like this picture. We would like to construct AS graph of the motion. Then we would like to determine the time meet. Time, we also require the time also for motorcycle to reach the position equal to 40 foot, that is at the end of the motion. Okay, so we have the VS graph. Okay, we would like to construct AS graph, starting with the kinematic equation of ADS equal to VDV. And then it means that the acceleration equal to velocity times the slope of the VS graph. Okay, we obtain the acceleration as a function of position, not function of time right now. Okay, the relationship of acceleration in terms of position by time the velocity, that is we know for any position to the velocity, the slope of VS graph. Okay, but now after we obtain the acceleration, it is the acceleration at any position S. Okay, but not at any time, because this is now we know the relationship between S and velocity. Okay, so from this equation we have two intervals of the position. That is the position measured from 0 to 200 foot. The motion is defined by this function, that is we have the velocity of 0.2 s plus 10 foot per second. Okay, and according to this relationship, we take the first derivative. We take the first derivative of this equation, okay, and multiply with itself with its velocity. That is the function of s. Okay, so this term is become 0.2, right? And then for when we multiply with the velocity, we obtain the acceleration function like this. And we can conclude that acceleration is equal to 0.04 s plus 2. You see that acceleration now for this problem, it is not a function of time, it is a function of s. Okay. And then we will consider for next period, that is for the position from 200 foot to 400 foot. You see, that is for this case, we know that velocity is constant according to the graph. In this period, velocity is constant along each position. Okay, so then we use this relationship and we will obtain the acceleration equal to 50. That is the velocity at any point times the slope of this graph. That is, this term is become 0. So then acceleration in this period is become 0 for any position. So then now we can construct the AS graph. Okay, this is the linear function. And we plot when s equal to 0, a equal to 2. When s equal to 200, okay, when s equal to 200, so what happened? A is equal to 0.04 times 200, okay, plus 2, okay, plus 2. Then it's become what? It become 10, okay, 10 foot per second square. That is this point, okay. And for the position of 200 to 400, acceleration is become 0 according to this. Okay, now we can construct the AS graph. Okay, so let's take a look for the time. For the time, if we would like to determine time, okay, we have to use the relationship of v equal to ds by dt. And according to this equation, we can rearrange from mathematics. We rearrange this equation to be this. We also have v equal to ds over v. Okay, because we have to know that from this problem, the velocity, acceleration, and acceleration, it is not a function of time. This is a function of position. Okay, as we know, this is a function of position. So then, when we would like to determine the time, okay, we have to rearrange this equation in terms of this. And according to this, we get dt equal to ds over 0.2s plus 10. Okay, so this term is the function of s. So then after we integrate both sides, integrate both sides, from time equal to 0 to time equal to t. So then from this, on the left hand side, actually it is the delta t, that is t minus 0. Okay, that is equal to t. And the right hand side, it is the integrate this term. Okay, so we have to recall the mathematics. Integrate this function, we have to recall the calculus. That's if we have the integration term like this, a and b are constant. So then if we integrate this term, we obtain 1 over b. Okay, we can review the mathematic, the mathematic formula for integration. Natural log of a plus bx plus c. Okay, so according to this, integrate this term So then this is A, right? And this is B. Okay. So for this case, it's become 1 over 0.2. We use the formula like that. Log 10 plus 0.2 S. Okay. Okay. Plus C, but for the this is the plus C is mean that we integrate without limit. Okay. But now we have the limit of integration from 0 to S. Okay. So then when we substitute S equal to 0 to S, okay, when we substitute S equal to S first, so 1 over 0.2 is equal to 5, okay, and log 10, right, log 10 plus 0.2 S, we substitute S into this equation, into this term. And then when, don't forget to substitute S equal to 0 into this term also. Then it's become 1 over 0.2 is become 5. And when we substitute S equal to 0, we have just log 10 like this. Okay. So then at S equal to 200 foot, okay. So time equal to this. We substitute S equal to 200 into this. Okay. We obtain the time equal to 8.05 seconds. Okay. This is for first interval. This is for first interval. That is, we know that at S equal to 200 foot. Okay. So time is equal to 8.05 seconds. But it's still not finished because we have the second interval, right? Okay. Okay. Now we have the time at S equal to 200 foot already. Okay. So then let's take a look for next period. That is, come back to this. Okay. Next period. That is, we know that for S equal to 200 to 40, we have V equal to 50, that is constant. In terms of S, it is constant. Okay, so according to this, we know that velocity function is equal to 50 foot per second. Okay, do the same thing. That is, we know that dp equal to ds over v. But now velocity is constant, that is 50, right? Okay, so then we integrate both sides. Okay, but we have to be careful that when S equal to 200 meter from the previous step, we know that time is equal to 8.05 seconds. Okay, so then we have to change the limit of integration to be this, that is 8.05 seconds to time. Okay, and we integrate this term. Okay, this is the constant. On the left hand side, we have delta t, that is t minus 8.05. Okay, on the right hand side, we obtain s over 50. S over 50. Actually, we integrate this term, right? It's become s over 50 from 200 to s. Okay, so then it's become s over 50 minus 200 over 50. This has become 4, right? Okay, so then we have this equation. After that, we can rearrange this equation to find time. Okay, so in this interval from s equal to 200 to s equal to 40, time is defined by this function as a function of position. Okay, so according to this, when we would like to determine time at s equal to 400 foot, substitute s equal to 400 foot to this equation, we obtain time equal to 12 seconds. Okay, This is the complete for this problem. Okay.